Hey everybody. I wanted to go ahead and make a first video for this year. I'm going to go through the review sheet that I gave you guys, which is not for a grade or anything like that, but if anybody is feeling like some of their skills aren't quite where they ought to be, then this is a good place to start, is make sure you know how to do everything on this sheet. Excuse me for a second while I adjust this camera. Anyway, I'm gonna probably split this into two videos. We'll do like 1 through 5 and 6 through 10 or something. But anyway, we should probably start with number 1, which I got the feeling most people were pretty good about, but let's go through it anyway. Looking at this thing is called a rational function because it's a fraction. The numerator is a function, the denominator is a function. And when you got a function that's built from two other functions and you're dividing them like this and it looks like a fraction, that's called a rational function. So to simplify this, what you want to do is factor. Now the numerator, since it's linear, is already factored as far as it can go. But the denominator, which is quadratic, we see that we can factor that down to x minus 4 and x plus 1. And then, now we see that we've got a factor of x minus 4 in the numerator and 1 in the denominator. So that common factor can cancel out, leaving me with 1 over x plus 1. And we did say in class that the one thing people might forget about here is if you want this simplified expression here to truly be equivalent to the original, then you have to remember that the original has two discontinuities because there are 2 zeros of the denominator. Down here we only see the -1 as a 0 of the denominator. We've kind of lost the information that would tell us that 4 is also a discontinuity. But this function, to be equivalent to the original, has to still be discontinuous there. So you have to just say that as a note. You have to say that x cannot be 4. And then as long as we include that domain restriction, then we're completely equivalent and that'll do it. That's my dog. He typically comes to visit during these videos. See him? There he is. Okay, back to work. That's number 1. Number 2 is going to be largely the same. It's just another rational that we need to simplify. The thing that was tough for us was a lot of people kind of forgot the formula for a difference of cubes. So the formula for a difference of cubes said that anytime you have a perfect cube minus a perfect cube, you just take the cube roots of those things. So a and b. Then you take the cube root, but you square it. You take the cube root of the other guy, but you square it. And in the middle, you take the two cube roots and multiply them together, ab. Then we said that the pattern of signs, like the plus or minuses, followed this mnemonic device of SOAP, S-O-A-P. That's not a P, P. So we said the first sign is the same, that's the S, the same. So because we're factoring a difference, we'll use a difference. Then the next sign is O for opposite sign. So since we factored a difference, we'll use a sum. And then AP is always positive. So this last sign on the end is always positive. Okay, so that means that for something like this, my two square roots are x and, or my two cube roots are x and 2. So my first factor will be x minus 2. And then the second factor will be an x squared plus 2 times x plus 2 squared, which is 4. So there's your factor form. And then in the denominator, again, we have that x minus 2 thing happening, which does mean we've got a common factor that cancels out, which means we can simplify this down to just the quadratic x squared plus 2x plus 4. But one more time, we sort of lost one of our discontinuities. You would expect this quadratic equation to have a domain of all real numbers, but you know that this original expression here had a domain restriction. X certainly could not be 2. And the fact that you're canceling that out doesn't mean that suddenly we can still be 2, not if we wanted to be equivalent to the original at least. So you have to go ahead and say, hey, oh, by the way, x is not allowed to be 2. Remember to include those domain restrictions. And then there you go. And again, just if anyone's curious, what that means is that our graph of this function here would just look like the graph of this parabola, which I don't know what it really looks like, but I know it's not factorable. So I don't know. I don't know if it hits the x-axis or not. I'm going to just say it doesn't. But it's going to be a parabola. But then the fact that x can't equal 2 means that wherever x equals 2, there'd just be a hole in it. And we should probably expect to see graphs like this every once in a while that are just sort of normal shaped graphs that just have holes popped in them because of these removable discontinuities. Okay, that's B and C. I mean, that's A and B. Let's go do C. And I would say the biggest thing for you to know about C is the numerator. It's kind of backwards. If you factor the denominator, you get x plus 5, x minus 5, because that's the difference of squares. And then in the numerator, you've got this 5 minus x. And those don't just cancel because, well, the terms are in the wrong order. And you can't just flip the terms around, not when you're dealing with subtraction. If this was a sum, if this said 5 plus x, then of course I could turn that into x plus 5. But with a difference, if you want to flip those terms around to an x minus 5, well, you kind of can. You just have to remember that what you now have is the opposite of what you used to have. Think of it like this. If you had 10 minus 3, that's 7. You want to turn that around and make it 3 minus 10? Well, you can, but that's going to be negative 7, right? So if you wanted to still have the same value, you'd need to sort of incorporate another factor of negative 1 that takes the fact that you now have the opposite and it makes it the opposite again and turns it back to normal. At least that's how I think about it. All right, anyway, in the denominator we've got an x plus 5 and an x minus 5. And just like the past three examples, that means that that factor cancels, generating a removable discontinuity. So I'm now just looking at negative 1 over x plus 5. And again with a domain restriction at positive 5. So again we see this whole function has two domain restrictions. It has the one that's listed at the end, but it also has the one we can clearly see for ourselves. We can see for ourselves that negative 5 is no good. And we're told over here that 5 is also no good. So we know that overall this simplified function has two domain restrictions, negative 5 and positive 5. I just don't have to list the negative 5 at the end because it's already obvious from the factor that's in our denominator. You just list the one that isn't obvious. You only list the one that we lost when we reduced. Okay, that's it. Number 2. Number 2's fast. I'm just going to tell you the answer, and we can decide if we care about going deeper later. But the Pythagorean identities were the ones that said that the sine squared of x plus the cosine squared of x would always equal 1. Then from there we developed a few other forms of this. We said that if we divided through by sine squared, then sine squared over sine squared would give us 1. And cosine squared over sine squared would be cotangent squared. And 1 over cosine squared would be secant squared. So that was an alternate form of the Pythagorean identities. Then we decided that since dividing through by sine squared worked out so well, let's divide through by cosine squared. So again, taking a and dividing by cosine squared, sine squared over cosine squared gives tan squared. And then cosine squared over cosine squared gives us a 1. And then 1 over cosine squared is, what are we dividing by? I think I screwed up. Because we're dividing by cosine squared. So 1 over cosine squared is secant squared. So my bad. That means in the previous one I made a mistake. We were dividing through by sine squared. 1 over sine squared is cosine squared, of course. I think I confused myself. So that's cosecant squared. Forgive me. By the way, I don't know how to edit. So I can't edit this video and go back and just make it look like I didn't make that mistake. So just bear with me. I just do these videos live and I don't feel like learning how to edit and I don't have any editing software. So if one of you kids wants to give me a lesson or something, then maybe I can increase the quality of these videos. But for now, the mistakes just kind of stay. Alright, anyway, those are the 3 Pythagorean identities, and honestly, I don't think we're doing anything with them anytime soon, so I'm not going to talk any more about them until I need to. So we move on to number 3. Oh, yeah, 3 was a big boy. 3 had multiple parts. You're supposed to be simplifying each expression, and this definitely might be one where you guys want to be paying attention because I don't think we did any of these in class. But let's go. These are rational expressions, and if I want to add or subtract them, I do need a common denominator. So for this, you'd want to find the least common denominator. And the least common denominator is typically what you get when you take one of every single factor that you see. So I see a factor of x plus h, I'm going to need that. I also see a factor of x, I'm going to need that. So this will be my LCD. Okay, so that means my first term here, it's missing a factor of x only. So I'll just multiply by x over x, and then I'll have the right denominator, x plus h. Then my second guy, he's missing a factor of x plus h. So I'll multiply that one by x plus h over x plus h. And that'll generate my common denominator. So this will just be the 1 over x. So multiplying this out gives me x in the numerator. It gives me a denominator of x times x plus h. Then here, I guess technically the one distributes in. So you get x plus h. In the denominator, you get x times x plus h. Alright, so notice I'm not really bothering to distribute the x in the denominator because I'd like to leave my denominator in factored form anyway. So what I tend to like to do is just make a big old fraction bar, and I now have my common denominator that'll just be the x times x plus h. And it's now just the numerator that I have to clean up. So clearly I have a term of x. Then it's going to be minus these terms, but do not forget, most importantly, remember, this binomial here is essentially in parentheses. So I'm going to be subtracting x and subtracting h. The biggest mistake I'm sure people are going to make here is they're going to just say minus x plus h. So now it's adding h when we should really be subtracting h. So remember, essentially what's happening is this binomial is in parentheses, and that negative would distribute onto it. That means what we're really doing in the numerator is an x minus an h all over x times x plus h. So that means x minus x, well, that just cancels out. The two x's cancel out, so we get a negative h in the numerator, which means we have negative h all over x times x plus h. And that would be the final form of this expression. It says right answers with positive exponents were applicable. So we're good here. That doesn't really mean anything to this problem. Let's go to B. Okay, so this is part B of number 3. And if you look at this, I see a fraction. But that fraction has fractions inside of it. So the numerator is a fraction. The denominator is a fraction. We call that a compound or a complex fraction. And probably the easiest way to do that is to maybe just think back to like 4th grade when you were learning how to, I don't know what the grades are really, but when you were learning to multiply and divide fractions, you guys learned that like 2/3, they would write it the old school way. They'd say 2/3 divided by 5/7. And how did you do that? Didn't you do it by just flipping this second guy and then multiplying? You just turned it from a division problem into a multiplication problem where you were multiplying by the reciprocal instead. And that gave you 14/15. So if you remember that idea, and if that idea made sense, I would attack this in the exact same way, because this compound fraction doesn't mean anything more than the numerator, which is 2 over x squared, divided by 10 over x to the 5th. So just flip and multiply like you used to do. So this will be 2 over x squared times the reciprocal of this, which is x to the 5th over 10. So if I'm going to do this problem super slowly, we would say, okay, this is obviously 2x to the 5th over 10x squared. And then from here, I can reduce these constant coefficients. This reduces down to 1/5. So this would be 1 over 5. And then I can reduce these x's. The fact that there's 2 x's in the denominator, 5 x's in the numerator, means 2 of them will cancel 2 of these, leaving me with 3 in the numerator, x cubed. So we're looking at a final answer here of x cubed over 5. Or I think I mentioned in class, I do tend to prefer just giving me the x cubed with a coefficient of a fifth. It doesn't matter. Both of these forms are fine, of course, but I sort of prefer just the look of 1/5 of x cubed. Now, I guess the question is, are there any domain restrictions on this? And of course, there are, because if you look back to the original form, there's a denominator here, and if that denominator ever equaled 0, we would be undefined. Then there's a second denominator down here, and if that denominator ever equaled 0, we would be undefined. At least we kind of get off easy here because both of those things equal 0 when x is 0. So the 0 of those denominators is the number 0. So technically we're not done when we say 1/5 x cubed. We're supposed to say 1/5 x cubed. Hold on, I'm going to get there. Hold on, I'm going to get there. Okay. Oh man. All right. Extend my little oval that I drew. And we got to put that domain restriction in there and say that x can't be 0. Because again, according to how I've written this, 0 is a totally fine input value for x here. If I plugged in 0, I would just get 0 and everything would seem hunky-dory. But if I plugged 0 into the original expression, I would be undefined. And I need this expression to be undefined for all the same values that the original guy was undefined, or else they're not truly equivalent. So again, we need that note on the end. Okay, that's 3b. Let's go do 3c as in cat. All right, hey, here's where it finally matters, that they're saying write your answers with positive exponents, because here's a couple of variables that have negative exponents. So how would you handle this? Well, the long way to handle this is to kind of break everything down and just be like, okay, this is 12 over 18. I can simplify that. This is x to the negative 3 over x, and I can simplify that. And then this is y squared over y to the negative 1, and I can simplify that. Now, do you have to do what I'm doing right now? You certainly don't. I'm just trying to drive home the point that basically what you've got here is 3 factors that you might be best off just considering these 3 factors separately. You've got the constants, then you've got the x's, and then you've got the y's. So let's clean all of those up. So these guys are both divisible by 6. So if I factor out 6, then I get 2/3. And then here, you can think of this in a couple of ways, but probably the easiest way to do it is to remember that if you've got the same base to a power divided by the same base to a power, then you just keep the base and subtract the powers. That's the rule there. So technically this would be x to the negative 3 minus 1, because downstairs we've got a 1. Okay, and then the y's would be a y squared minus negative 1, which has me thinking that we're about to get a 2/3 times x to the negative 4 times y to the positive 3. Right, and again, it says up here, remember, give your answers with positive exponents only, and this x has a negative exponent. So the way you would clean that up is keep your 2/3. Negative exponents mean that you're taking the reciprocal of your base. So you'd go, okay, I guess my base is 1 over x now. And now the 4 is not negative, but positive. And then the y cubed was always fine. So that means I'm looking at a 2/3. And then this 4 essentially just affects the top and bottom. You get 1 to the 4th, which is 1. You get x to the 4th, which is x to the 4th. And then this is y cubed. And since everybody else is a fraction, let's just put this guy over 1 so it looks like a fraction too. And finally, just multiply everything in the numerator. So 2 times 1 times y cubed is 2y cubed. All over 3 times x to the 4th times 1 is 3x to the 4th. Alright, that's it. And I'm by no means saying that the way that I just did this problem is what you have to do. I'm just kind of taking it real slow and making sure that everybody remembers why everything I'm doing is what I'm doing. With negative exponents causing you to take the reciprocal of the base and stuff like that, You guys, I'm sure, could move pretty efficiently from the original expression straight down to here without showing much work at all, and I would be fine with it. I'm showing the work because I'm the teacher. I'm showing the work to make sure that everybody understands what all the steps would have been. Okay, let's do part D. All right, for part D, I don't know, treat this kind of the same as the last one, where you treat the constants as their own thing. So you just do 4 times 5, you get 20. Then treat these factors or these powers of a as their own thing. So 5 times 4 is 20. Then we're multiplying that by a to the 2/3 times a to the 3/2, which means keep that base of a and add these powers. So it'll be 2/3 plus 3/2. So that means we've got a little mini problem on our hands. So let's kick off to the side or kick out to a piece of scrap paper or something. But we need to now do 2/3 plus 3/2. That means we're looking for a common denominator, which I hope is obviously 6. So this guy needs to get hit by a 2/2. And this guy we're going to hit with a 3/3. Which means if I express these fractions with a common denominator, then this guy's denominator is going to be 6, and his numerator has to be 4. And 4/6 is the same as 2/3, so we're good to go. And then here, do it again. You get a denominator of 6 and a numerator of 9, and 9/6 is the same as 3/2, so we know we're good here. Then to add fractions, of course, you keep the same denominator of 6, and you only add the numerators to get 13. So I'm getting 13/6 for this. And then we're done. There's nothing more to do from there. So we get 20 as a coefficient on the exponential a to the 13/6. And that answer is fine. And just for the sake of argument, I would say if for a certain problem I told you to give your answer in radical form instead of exponential form, then remember that 6 could come out and be the index number of a root, meaning we're taking the 6th root of a to the 13th. And then I don't want to go too nuts here, but at the same time, yes, I do. You guys are coming into calculus and you better know everything you're supposed to know. So this could be simplified because I'm taking the 6th root of something to the power of 13. That could certainly break down and be simplified. So this is like 20 times the 6th root of, well, maybe think about it like this. What if I went a to the 6th? Wouldn't the 6th root of a to the 6th clearly just be exactly a? So that's 6 of my a's covered, but I still have 6 more. And that's still only 12 a's, and then I could still have 1 more a. And so essentially now I can simplify, this part and this part, but this guy will still be a 6th root. So maybe the best answer here would be 20, and then this would be plain old a. Then I get another factor of plain old a, and then I have one last factor of the 6th root of a. So if you were going to express this in radical form, I would expect that you could pop out this factor of a squared and be left with one factor of the 6th root of a. That would actually be the best possible answer if we were in radical form. And honestly, for that reason, that's why exponential form is probably better, because it doesn't really matter up here. If your numerator is greater than your denominator, you just leave it alone. But hopefully we see that those two expressions are equivalent. One is just the rational exponent form, and this is the radical form that has been simplified as much as possible. Okay, so that's 3D. Let's check out 3E. And this don't look too bad. So the only thing I would remind you here is this power of 3/2, because it's applying to everything in parentheses, it would apply to the 4 and the a to the 5/3. So technically it should probably look like 4 to the 3/2 and then times a to the 5/3 to the 3/2. So we have to apply that power of 3/2 to both. So to simplify the 4 to the 3/2, you kind of have to think about this thing as a radical. So the 2 means I'm doing a square root. So I'm doing the square root of 4. Then the 3 is a power. Now the 3 could go on the inside or the outside, but if I had to cube the 4 and then take the square root, I might end up with a really large number whose square root I don't know anymore. And right now the square root of 4 is easy as pie. So I definitely would rather put this 3 on the outside and cube after square rooting. That just makes life easier. Over here I have power to a power, so I'm just going to multiply these, and I would get a to the 15 over 6, but probably a better way to think about this is... Okay, bad dog. Or good dog, depending on how you look at it. Maybe he was just protecting me, right? Isn't that good? Anyway, what was I saying? 15, he's back. 15 over 6, which is going to reduce down to 5 over 2. Okay, so what's this? Square root of 4 is 2, 2 cubed is 8. So you're getting 8 as a coefficient on a to the 5 halves. Or, if you really wanted to give it in radical form, that would be 8 times the square root of a to the 5th. Let's kind of go a to the 5th. So that means this is simplifiable too. How would you simplify it? Well, you've got an a squared and another a squared, then you've got another factor of a. So if you took these square roots separately, then you're going to get 8, and then a plain old a, and then another plain old a, but then a root a. So that would be 8a squared root a. So in radical form, it's that. In exponential form, it's that. I will happily accept either form. Unless I specifically ask for one or the other. If I ask for one, give me that one. If I ask for the other, give me the other. Alright, that's 3e. How about 3? Oh, 3f. We finally get something fairly easy. So hey, we're evaluating a log, and I don't see a base. So we talked about how when you don't see the base of a log, it's understood to be a base of 10. And hopefully you guys remember what I said about this. The question that a log is asking you is it's asking you, hey, to what power should I raise 10? So that the result will be 1 over 100. And so probably what you should do to think this through is think about, well, 100 is just 10 squared, isn't it? So 1 over 100 is 1 over 10 squared. But because the 10 squared's in the denominator, that's essentially just 10 to the negative 2. 10 to the negative 2 would be 1 over 10 squared. That would be 100. So essentially, I'm asking you, hey, what power do I want to use? And we can see that clearly that power is negative 2. So that means the value of this particular log is negative 2. And that's it. What about g? G is even easier, because g is asking you, what is the log base e of e to the 7th? So again, if I was trying to find this thing's value, then they're just asking me, hey, e to what power is equal to e to the 7, at which point it becomes pretty clear that the mystery power that we're looking for is the number 7. So we're done. So this log has a value of 7. And that's it. H. H is another easy one because I've already talked our way through this. If you were going to simplify this, remember the denominator becomes a root. We're doing a cube root. And we're doing the cube root of our base, which is 27. And then you've got your choice. Do you want to square the 27 and then take the cube root? Or do you want to take the cube root and then square the result? Clearly squaring the result is the smarter thing, because cube root of 27 is 3. And I can square 3 and get 9. That's it. I. Alright, I is tricky because I is saying, to what power should I raise 1/2 to get 8? And it might feel like there is no power of a half, because if I raise a half, if I square it, it goes to a quarter. If I cube it, it goes to an eighth. As I raise it to more and more powers, it just keeps getting smaller. Seems like it's not going to approach 8. But of course it does. We just want to get down to a common base. So maybe you'll think of this in a couple steps. 8 is pretty clearly 2 cubed, I hope. At which point you then remember, oh, but 2 is just a half to the negative 1. So if I frame this as a half to the negative 1 cubed, then that's 2 cubed, that's 8. And so again, we're in a place where we can see that, you know, what power of a half do I want? I want the negative 3rd power of a half. And then we can see our final answer is negative 3. So up here, this log expression has a value of negative 3, which I think makes sense now. You'd say, okay, to raise a half to the negative 3, I take the reciprocal, of the base, I get 2. Then I cube it, 2 cubed is 8. So we're good. Okay, I think there's a j. Yeah, oh, j is the easiest of all. This is lovely. So they're saying log base e of 1 equals what? So they're asking you what power of e would make 1. And the answers here, this is the same as anything else, right? 7 to what power makes 1? 19 to what power makes 1? Isn't the answer that anything to the power of 0 is what makes 1? 19 to the 0 makes 1. So e to the 0 must make 1. So the ln of 1 is 0. In fact, the log base anything of 1 is 0. That's a log rule, that log base b of 1 is always 0, no matter what value of b you choose. So that's a piece of cake. Does that bring 3 to a close for us? I think it does. So let's talk 4. So number 4, you're given a couple of functions, and if you don't remember what this notation means, where it says h of g of x, this was called function composition. It's where you sort of evaluate the inner function first, then you take the output of the inner function and you plug it into this outer function and you see what you get. So what's h of g of x? I have no idea. Yes, I do. Okay. Because for h of x and g of x, those are just defined by function rules. F of x is just defined as a set of ordered pairs. That would be a little weirder to deal with if we were doing this. But to do this, you just literally take g of x and cram it inside of function h. So if function h is my outer function, then I'll go x squared plus 5. But x is no longer x. X would be the entire function g of x. So it's like we're getting x squared plus 5. But we're taking this radical function, root x minus 3, and we're plugging it in where x used to be. So we get the entire function g squared plus 5. And then you just simplify this. Now we're squaring a radical, so that gives us x minus 3. Sure. Then we're adding 5, and that gives us x plus 2. Alright, and I don't want to get too in the weeds on this, but technically our domain here is definitely restricted, because when we do function composition, the inner function's domain has to be respected, and this thing being a radical function, x would have to be at least 3, right? 3 or greater. So this guy's going to have a domain where x can only be on the interval of x is bigger than 3, so 3 to infinity. So I'm not sure you necessarily have to list that whole sort of domain thing, but I'd hope that you understand what I'm saying a little bit. Is the way this function is defined, like I can't plug in 0. Think about it. If you plug in 0, then you're taking the square root of something that's negative, which generates an imaginary output, which means we're already out of the domain of real numbers, which means that value is immediately just kind of discarded from the domain of this composite function. So technically we get x plus 2, but if you were going to graph it, instead of getting the entire function x plus 2, which would be, y-intercept at 2, slope of 1, instead of getting this big beautiful line that runs forever in both directions, we would have a firm endpoint at 3, 5 or whatever here, and we would only get this right hand side. So it's really like we would get a ray instead of a whole line. All of this would be deleted. So if you were truly trying to write the rule for the function that represents this composition, you couldn't just say x plus 2, because you'd be writing the rule for an entire line that has a domain of all real numbers. We need to stipulate that our domain is that we actually only want the piece that goes from 3 to infinity. And I don't know if that made sense or not. That was one of the more difficult topics from last year in pre-calc. So just ask me about it if you're iffy on it. Okay. I don't think I've got my slides ready. I don't, of course. Give me a sec. Okay, I'm back. That was A. Let's go do B. B is actually a little easier, because in B, we're not trying to write a function rule in terms of x anymore. We're just trying to actually evaluate at -2. So just think of this as two steps. You essentially just have to evaluate the inner function first, which is h of negative 2. So go grab function h, which is x squared plus 5, and plug the negative 2 where the x used to be. That gives me 4 plus 5, which is 9. So that means now that g of h of negative 2, well, if h of 2 is 9, then you're just trying to find g of 9. So just plug 9 into function g, which gives you the square root of 9 minus 3, aka root 6. And that's it. That's the answer. G of h of negative 2 must be the square root of 6. Okay. C. They're asking you to find the inverse of function f. Hopefully you remember that an inverse function is the one where if the original function f of x gives a y value, the y value, then that means that the ordered pair x and then y is on that graph. Well, the inverse function by definition is the one where if you let y be the input, then the output is x. All the ordered pairs just reverse. And since our function is defined solely as ordered pairs, it's pretty obvious that the inverse of f is just going to be the set where all three of these ordered pairs reverse. Instead of 3, 5, it's 5, 3. And instead of 2, 4, it's 4, 2. And instead of 1, 7, it's 7, 1. So that's it. That's it for C. Piece of cake. Okay, and lastly, in part D, it says to find the inverse of function g. Now, like a real function, how would you find the inverse? You switch x and y, and then solve for y. Fill in the blanks, and then actually do it. So they want us to actually do it. So when they say g of x, that's just fancy function notation. That essentially just means y, and that equals root x minus 3. So if I switch x and y, then all the y's turn into x's, and all the x's turn into y's. So in the case that we had more than one x, like in a quadratic, if you had x squared minus 4x plus 6, if you were trying to find the inverse of that, then of course this one y becomes x, but all the x's become y's. So you'd go y squared minus 4y plus 6, and then you'd have to find a way to isolate these y's and solve for y. Luckily, that's not the situation we have. So for us, we just have root y minus 3. And this seems to me that I should square both sides, which will land me on an x squared. That equals y minus 3. Then I should just add 3 to both sides, which will give me an x squared plus 3 that equals y. But wait a minute, what's y? Y is really the inverse of g of x. So let's switch back to that fancy function notation. And we can say that our final answer is that the inverse of g is x squared plus 3. Or is it? And the answer is, of course, it isn't, because inverse functions have to inherit their domains from the original functions. So hopping all the way back, way to the beginning, let's think this through. Function g of x has a domain of only the things greater than 3. Remember, 3 to infinity, we already talked about that. But somewhat more importantly, it has a range of, well, let's see, we didn't get shifted up or down, right? And radical functions start at the origin and go like this. At least if you're talking about the parent function, root x, it would look like this. So root x minus 3, well, that would just be kicked over to the right? So suddenly would be at 3. So I'm just going to move the axis. And we'll say this is x equals 3. So our domain is only the x is bigger than 3. Our range is only the y is bigger than 0. Well, that means that my inverse function, it would take on this guy's range as its domain, and it would take on this guy's domain as its range. Well, x squared plus 3 would naturally have a domain of all real numbers. So again, we find ourselves in that position of having to sort of artificially restrict our domain and saying, hey, the rule is x squared plus 3, but only if you restrict the x's to the set of x's that are greater than or equal to 0. So what you're getting then is only the right-hand side of a parabola, which makes sense if you think about it, because the original graph was only the top half of a parabola. And maybe you remember that geometrically, a function and its inverse are the reflected images of one another over the line y equals x. And what do you think happens if you take the top half of a parabola and reflect it? You indeed get only the right-hand side of a parabola. This guy was shifted over 3, so this guy will be shifted up 3. And if I'm only reflecting the top half, then I only get the right half. To me, this all actually makes perfect sense if you stop and think about it, both sort of algebraically and visually. Then we understand why we need to restrict that domain, because we don't want the whole parabola, we only want half. That's pretty important what I just said. I hope that made sense. Okay, that's the end of 4. How's 5? Oh good, 5. I don't think I care about 5, and I don't think I'll care about 5 for a while, but I will eventually care about 5. But here's the deal. It says right here, this little symbol means sum. And these little numbers at the top and bottom, that's just kind of like a counting index. So it says, hey, start by letting n be 2, and then let n increase by 1 until you get to a maximum value of 5. So essentially this thing is saying, let n equal 2 and calculate some answer, then add to that what you get when n is 3. Then add to that what you get when n is 4. Then add to that what you get when n is 5. And so because these numbers are nice and small, we can see that all we're really doing is adding up 1, 2, 3, 4 things. And those things are whatever 3n minus 6 is. That's my expression. So they essentially are just telling you to evaluate 3n minus 6 4 times. Evaluate it at 2 and 3 and 4 and 5. And then add up all the results. So that would mean at 2, we're going to do 3 times 2, take away 6. Then we're going to do 3 times 3 and take away 6. Then we're going to do 3 times 4, and you guessed it, take away 6. Then we're going to do 3 times 5 and take away 6. Then just evaluate all those and add them up. So 6 minus 6 is 0, and 9 minus 6 is 3, and 12 minus 6 is 6, and 15 take away 6 is 9. So that funny expression up here literally just represents the sum of these numbers, which is, let's see, 3 and 6 makes 9, 9 and 9 makes 18. That's it. That's all. All right. I do think this is a good stopping point. This is a 42-minute and 35-second video. So that's the first half of our review sheet. I'll make a video for the second half now too, because I'm sure you've got some questions from there. Again, if this was useful to you, let me know. Tell me. Put a comment down that says it helped you, or just in class, just say, hey, thanks for the video. That was actually really helpful. Something like that. But this is a lot of work for me. So if you want me to keep doing it, then tell me it's worth it for me to do it. All right, thanks. See ya in class. Goodbye.